Okay, let's go back to today's contents. Yes, as I said at the beginning, today's topic is about one is auditory sense, and one is a visual sense. And the contents of today's topic is firstly about the fundamentals of the biology of auditory, fundamental of the biology about the visual, and the second half is engineering part of auditory, engineering part of the visual sense. Okay, and auditory senses, one is analysis, engineering analysis, and engineering application. And the visual sense is almost engineering applications, or the supplementary method of lacking of sense. Supplementary method of lacking sense. Okay? わかる？わかるね。で、じゃあ、what is the common thing between auditory sense and visual sense? As I said last week. Huge. Common.
Optical. No, it's difference.
Difference. Common. Item. Visual to art. Yes, remote sense. Remote sensing. Auditory is also remote, visual is also remote sense. And the difference is, as you said, auditory is mechanical, stimulus. これ optical stimulus. Mechanical stimulus, optical stimulus is a different thing. Yes, so the first part, the auditory sense. Ear, human, firstly, ここにあるのは、sound. What is sound? Sound is propagation, the thin dense wave in the air. It means it has some speed of movement, and it is saying that the longitudinal wave. What is a longitudinal wave? Xu Chen, what is a longitudinal sense? Longitudinal wave.
It's direction. How to say? It's not the same. It's like this crossed.
それはロンギチューディアルっていうのはこのアクシアルウェーブでしょ。それからパーペンディキュラーウェーブっていうのはパーペンディキュラリーウェーブ。Earthquake is also two different waves. So this longitudinal axial wave and this perpendicular wave.
Direction is different.
Yes, direction is different. The transition movement and the transition movement vibration or the perpendicular vibration is different. In air, sound is in the air and thin dense wave. It means some part is becomes very thin and density and high density, low density, and this wave is transferred from one place to the other while moving, while transferred. So therefore it is said in thin dense wave or longitudinal wave. Okay. This is mechanically the thin dense vibration. And ear. In ear, they are separated into three parts. First is the ear flap, and ear canal, some kind of tube, and the middle ear is this drum, and three main bones. Three main bones. It is here the malleus, incus, stapes is three bones. Series of three bones is here. これね。これとこれとこれね。Three bones here and So finally, the some third part is this cochlear. で、なんかを見るといいんだけど、これか、まあ、はい。
The ear has three parts: the outer ear or auricle, the middle ear, and the inner ear. The auricle, the visible part of the ear, collects sound waves and directs them to the auditory canal. The auditory or ear canal is lined with cilia and ceruminous glands. The earwax from the ceruminous gland and the cilia protect the ear from entry by foreign matter. The thin tympanic membrane separates the outer ear from the middle ear. Sound waves cause it to vibrate. The three tiny bones of the middle ear are the hammer or malleus, anvil or incus, and stapes or stirrup.
今言ったように、ここのまず first part is capturing the sound, and it is transferred this canal, and this eardrum, and series of three bones makes concentrate this energy and transferred into this vibration. This takes vibration finally. Okay, it is concentrate as a mechanical vibration here.
These bones pick up the vibrations from the tympanic membrane and transmit them to the inner ear. The eustachian tube of the middle ear opens into the pharynx and permits air pressure to equalize between the ear and the outside air. The inner ear is maze-like, consisting of bony and membranous structures surrounded by fluid. The semicircular canals are fluid-filled bony loops that help maintain our body's balance. The cochlea is a fluid-filled, snail-shaped structure that houses the organ of Corti, the true organ of hearing. The fluid aids in the transmission of the vibrations. The organ of Corti changes the vibrations into nerve impulses that are picked up by the auditory nerve.
っていうのは、ここに、これはまあメカニカルバイブレーションがスティムレスで、これは、コクリアで、this announcement set, this is like a tube, but filled by liquid. Filled by liquid. This is a cochlear is summarized with this kind of tube, but this is one chamber, the other chamber, and this membrane is at the center. And on this center, some kind of nerve cell is here. And the vibration is transferred to around this canal, and then some nerve cell is detect the wave, and then by using this wave, this nerve cell is generates some impulse, and this signal is concentrated and transferred to the brain. This is a system. So therefore, this cochlear system is making from transfer the mechanical signal to the electrical signal. Okay? And then also, as I say, the following. This is the frequency distribution can be captured by this system. Frequency, that's low sound, high sound is separated. Which portion is vibrated more. So maybe you may estimate the longitudinal tube, the low frequency vibration is transferred to the top, but high frequency sound is only at the beginning part, entrance part. So therefore the frequency, sound frequency, and which part is most vibrated is decided by this cochlear system. Okay, so this system discriminates the which frequency sound is captured by ear is detected by this cochlear system.
Sound waves are collected by the auricle, or outer ear, and sent to the auditory canal, tympanic membrane, ear bones, and then to the cochlea, where the vibrations are changed by the organ of Corti to nerve impulses and transmitted by the auditory or cochlear nerve, the temporal lobe of the brain, for interpretation.
これはベースメントですね。OK。で、セカンドパートです。コクリアですね。で、コクリアシステムっていうのは、だからこれが、メカニカルバイブレーション is this input and this chamber is the upper chamber, lower chamber, upper chamber and lower chamber, and also the middle chamber is also here. And here is some the nerve system, and this nerve cell has some hairs. And this hair is waved by moving of the fluid liquid. So therefore, this wave, the hair waving makes the pulse, electrical pulse generated by this nerve cell. っていうのは、ちょっとそれはどこでわかるかというと、例えばこれか。
Welcome to 2-Minute Neuroscience, where I simplistically explain neuroscience topics in 2 minutes or less. In this installment, I will discuss the cochlea. When sound waves travel through the canal of our ear, they hit the tympanic membrane or eardrum and cause it to vibrate. This vibration prompts movement in the ossicles, a trio of tiny bones that transmit the vibration to a structure called the oval window, which sits in the wall of the cochlea. The cochlea is a tiny coiled structure in the inner ear that resembles a snail shell. The interior of the cochlea consists of 3 fluid-filled canals that run parallel to one another: the scala vestibuli, the scala media, and the scala tympani. The scala vestibuli and scala tympani contain a fluid called perilymph, and the scala media contains a fluid called endolymph. When the oval window is depressed by the ossicles, it creates waves that travel through the fluid of the cochlea. These waves cause a structure called the basilar membrane to move as well. To visualize the function of the basilar membrane, it can be helpful to imagine the cochlea uncoiled. When waves flow through the fluid in the cochlea, they create small waves within the basilar membrane itself that travel down the membrane. Different sections of the basilar membrane respond to different frequencies of sound, and as the waves progress down the membrane, they reach their peak at the part of the membrane that responds to the frequency of the sound wave created by the original stimulus. In this way, the basilar membrane accurately translates the frequency of sounds picked up by the ear into representative neural activity that can be sent to the brain. The translation of the movement of the basilar membrane into electrical impulses occurs in the organ of Corti, which is the receptor organ of the ear. It sits atop the basilar membrane and contains receptor cells known as hair cells. Hair cells are so named because protruding from the top of each cell is a collection of small hairs called stereocilia. When the basilar membrane vibrates, this causes movement of the hair cells and their stereocilia. Movement of the stereocilia opens ion channels and causes the release of neurotransmitters to propagate the auditory signal to the vestibulocochlear nerve, which will carry the information regarding the auditory stimulus to the brain to be analyzed and perceived.
ということで、だからここにメンブレンのところに、さっきの図だとこういう、ナーブセルがあって、でここにヘアがこうあって、でここの、ミドルチェンバーのリキッドがなんかこう動く。By this vibration of this membrane, the liquid is a little bit moved. So therefore, this hair is waved. By waving this shell, this nerve cell generates a pulse. ということで、この along this canal, the pitch frequency is most vibrated, is the preliminary decided. For example, this part is a high frequency sound is most vibrated. This part is the middle frequency sound is vibrated. And the end of this canal part is lower vibration sound is the most vibrated. So therefore, this canal system is specific frequency is discriminated along this canal. Okay? それは今ここで、話をしたと思うんで、OK? いいですね。 で次のページがまあフォーラクセンっていうのはまあいいとして、だから not only this but yes this part some sound is this part, for example, one part is the level, the other part of the level is different. So along this, the magnitude of waves is low frequency sound is looks like this. So therefore, the high frequency is most vibrated in this part, and in other case, high frequency sound is looks like this. So therefore, the high frequency sound is most vibrated at this portion. So all of the nerve cell is located along this canal, and the pattern of the output signals, electrical signal is different depending on the frequency. This looks like this. This is a little bit low frequency. This is a high frequency, a little bit higher frequency. So therefore, this black line or this red line is stimulation generated pattern is different depending on the sound. でこの今のところがこの Fundamentals of Biology ね、Auditory Sense Fundamental of Biology で This part is engineering analysis part. One of engineering analysis, mechanical engineering analysis part is FEM, finite element method. So this ear drum and also three small bones serially connected is the model like this small part. Small element has some the stiffness or compliance, spring damper characteristics, and then the mechanical engineering analysis will be done by using each element's movement, each element's connection is modeled. So when some sound is applied to here, which kind of movement is happened at this part is simulated. Yes, these three bones is movement of these three bones is looks like this. Simple model is this first bone is rotated around this axis. Second bone is also rotated around this axis, and then this third bone is this kind of movement is happened. So the one example of the mechanical analysis about 10 years ago is looks like this. なんかsound is applied here, and which kind of deformation, which kind of noise, which kind of frequency transition is simulated by using the FEM method. というようなやつですね。で、the other mechanical engineering analysis is this Cochlea. Cochlea is modeled one-dimensional tube, looks like this, one-dimensional tube, and this is the middle part is a membrane, some part, and the upper chamber and lower chamber is filled by some liquid. So therefore, this to analyze this, and the stimulus is given at this part. The third bone is vibration is the input part, and so this is the mechanical engineering part, the mechanical dynamics part of this tube, and also the fluid dynamics is also parallelly analyzed. The Euler equation or Laplace equation is applied to this tube's mechanical dynamics. And then analyze which kind of frequency is applied and which part is the most vibrated, In some cases of the, for example, the 1 kilohertz vibration is inputted, which part is the most vibrated is simulated. Looks like this. This is a これが input port is look like this. This is a 0 millimeter, and the cochlear's length is about 35 millimeter. And along this tube, which part is most vibrated is simulated. 1 kilohertz is this part at about the 20 millimeters from the input port is the most vibrated by the 1 kilohertz input wave. It is almost matched to the realization, actual phenomena. Okay, 1 kilohertz is look like this. 20 kilohertz is look like this, and the which frequency is most vibrated, and the every part is examined by this dynamic simulation, and it is result is look like this. This is almost matched to the actual experimental result. っていうようにメカニカルエンジニアリングアナリシス is also used. この these two is the analysis part here. And the next part is some the auditory functions auxiliary system, substitutional system. Okay? One is assist device. One is other sense is used in place of the auditory sense. One is tactile sense is used in place of the auditory sense. One is visual sense is used in place of the auditory sense. Okay? So the まあ補聴器っていうのはよく使われまあ maybe you know the hearing aid. Some the microphone is here and some the sound processing and then the tuning the sound and the inputted into the ear is many some of the elderly people is using, but the most diseased people is using the artificial middle ear, artificial ear and the cochlear implant. What is the difference? The artificial middle ear and artificial cochlear implant. It's the cochlear is damaged or not is the difference. For the middle ear implant, the present cochlear is used, but this eardrum and 3-bone serial connection is damaged. So therefore, in place of this part, the middle ear implant is used. この middle ear implant case, the cochlear is the present cochlear is used, but this capturing the sound and concentrate as some typical vibration to the cochlear, this part is damaged. So therefore, the mechanical vibration system is artificial mechanical vibration system is implanted inside of the human body. それは、例えばどれを言えばいいかな。こんなもんか。ちょっと待って、よくわかんないけど。
The vibrant sound bridge is an alternative to conventional hearing aids or bone conduction devices. The vibrant sound bridge middle ear implant system consists of an externally worn audio processor and an implant which is placed surgically under the skin. The audio processor is held in place by magnetic energy and can be worn comfortably under or over the hair. Sounds are picked up by the microphone in the audio processor. The audio processor converts environmental sounds into electrical signals. The electrical signals are transmitted through the skin to the implant. The implant relays the signals down the conductor link to the floating mass transducer, abbreviated FMT. The FMT converts signals into mechanical vibrations, which set the structures of the middle ear into motion. The FMT has a frequency range of up to 8,000 Hz. The versatility of the FMT has led to a variety of surgical applications known as vibroplasty. The incus vibroplasty, for example, involves affixing an FMT to the incus. This procedure is a treatment for sensory neural hearing loss.
まあいいや、このシステムは、this system is existing 3-bone system is also used, but it is not correctly worked by some the muscle problem or ligament problem or something, or eardrum problem. So therefore, the existing 3-bone system is used and some weight is attached, and then the weight, the vibration is makes some this bone the movement. But other system is also the completely replacing or some the current bar is used to the mechanical vibration system is also attached. Yes, mechanical vibration system or something is attached like this. ちょっと他のやつも多分ね、これはどうかな。
Normal hearing is the result of your natural anatomy working in harmony to convert sound waves into electrical signals, which are transmitted to the brain. With sensory neural hearing loss, the hair-like cells of the cochlea are damaged, which makes it more difficult for the cochlea to convert these sound waves, diminishing your ability to hear. Esteem is the only FDA-approved, fully implanted hearing device. This means that, unlike a traditional hearing aid, there are no external components and nothing in the ear canal, making Esteem invisible and free of daily maintenance. Esteem is designed to work with your natural anatomy. It does not use a speaker or an artificial microphone. By utilizing the natural structures of the outer ear, the ear canal, and the eardrum, background noise, distortion, and acoustic feedback typical of conventional hearing aids are reduced. The Esteem sensor converts vibrations from the eardrum and sends electrical signal.
これはここをカットしてしまって、このバーでここをプッシング。で、これモーターがあって、ここのバーでこうプッシングしてると。だから this part is not used. But some part is sensed by this, and then this motor or some vibrator is makes this rod vibrate this, the pushing this third bone. Okay? This system is also there. これが、ミドルイヤーのリプレイスメントね。ミドルイヤーパートリプレイスメント。Some vibration これか is exciting this part っていうのがこんな感じです。というわけで、次のパートは、コクリアインプラントね。Cochlea is totally damaged. So therefore, the stimulus electrode is inserted along this cochlea. The electrode is inserted along this canal tube. この中にね、これだから this part is electrode. So for example, the 22 electrode along this canal is inserted. 22 frequency sound is stimulated to this canal system in this case, in some case. So I will show some. 例えばこれか。これはちょっと待って。 これは入れてるとこだからちだ先に。
The synchrony cochlear implant system is designed to restore hearing to individuals with severe to profound sensorineural hearing loss. Individuals with this type of hearing loss have serious difficulty hearing and may not hear at all, or may only be able to hear very loud sounds. The synchrony cochlear implant system consists of the externally worn Sonnet audio processor and the internal synchrony cochlear implant. The Sonnet audio processor is worn comfortably behind the ear. The synchrony implant is surgically placed under the skin, and a flexible electrode array is inserted into the cochlea. The cochlea is the part of the...
これはだからこういうシステムは inserted along the cochlear's chamber, and this part is an electrode to make the bolt or some pulse is generated here.
Inner ear that converts sound waves into nerve signals, which the brain processes as hearing. The apical region of the cochlea is responsible for detecting low-pitched sounds, while the basal region is responsible for detecting high-pitched sounds. The cochlea is lined with thousands of sensory cells, known as hair cells, which detect sound waves and send sound information as nerve signals through the auditory nerve to the brain. For individuals with severe to profound sensorineural hearing loss, most of these hair cells do not function normally and are not able to send these nerve signals properly. A cochlear implant system bypasses these non-functioning hair cells by using electrical pulses to send sound signals directly to the auditory nerve. To achieve this, the Sonnet audio processor detects environmental sounds and digitally converts them into coded electrical signals. Sonnet transmits these signals through the skin to the implant by a communication coil. The implant translates these coded signals into electrical pulses, which are transmitted along the electrode array to stimulate specific locations of the cochlea responsible for specific pitches. This targeted stimulation across the whole cochlea provides a more accurate pitch perception for better sound quality. By mimicking the natural function of hair cells, these pulses can deliver sound signals directly to the auditory nerve. These signals are then transmitted by the auditory nerve to the brain, where they are interpreted as sound.
いや、まあこういうような感じで、だから outside body's processing part, sound processing part of this coil で some signal is transferred, and then this makes some stimulus, electrical stimulus to this electrode, and then this electrode is makes stimulus to this nerve system, and then the nerve system's axis or something is used to transfer to the brain. というわけでしたということで、これが、例えば inserting this, the looks like this. From here, along the cochlea, this electrode is implanted inside the cochlea. It looks like this. This is during the surgical operation. It looks like this. Checked the location or the shape of this. ですね。はい。です。で、こういう感じですけど、What is the cost? This is the surgical cost, of course, the surgical cost and the surgical medication during the operations, and also this device's cost, the device cost itself, and also the staying in the hospital, examination, the hospitality or rehabilitation is necessary, how much cost it takes. How about this cochlear's implant price? What is the price of this system? Your estimation. How much is it? 50万円、100万円、200万円、300万円。いくらでしょう？ How much is it? はい、シューチェン。How much? 200万円。まあ手術の費用は、オペレーションは、サージカルオペレーションは30万円ぐらい。で、サージカルオペレーション30万円。で、このセットは、まあ大体270万円、300万円ぐらい。300万円。で、入院の費用は大体100万円ぐらい。で、合わせるとトータルすると、これはもう400万円ぐらいかかるよね。400万円。でだけどまあこれは一応ヘルスインシュランスで決まってるから in Japanese people はヘルスインシュランスなので大体自分の pay by myself is about 十数万円から数万円 several 万円 only pay for this implanted system in Japan です。はい、わかりました。ということで、今のはだからこれはもう完全にインプラントシステムでしょ。で次は the in place of other sense でタクタイルセンスで聞くっていう、例えばタクタイルボコーダーとかタッチボイスっていうのがあって Yes, this is 3 lines of each of it is some the needle to stimulation, mechanical stimulation pin is here, and then if you touch the fingertip on here, some sound is captured by microphone, and the signal processing, and using this 16 kind of frequency vibration separation method or something, and then some sound is given the user by vibration. It looks like this. And also that is a type of the vibration, skin sensations understanding of voices. And then the next part is the visual information. In place of the visual information, like this kind of the hand gesture, finger gesture, displacement robot, and the displacement finger, displaying finger. This robot is developed for more than 40 years ago, about 50 years ago. Balloon robot is developed in Japan. Looks like this. ちょっとこれ見る。
虹のアーチ。見上げるように新しく創作されたソフトで美しいロボットで。
バブルーンロボット。ここで。本当
はママに叱られますけど、ちょっぴり内緒で。お目目を見てください。パチパチパチ。またまた。パチパチパチ。あったんでできるかな。
ここで、フィンガージェスチャーしたっていう。
バボット感でございます。私いろんな国の言葉でご挨拶できるんですよ。いらっしゃいませ。ハロー。シェイシェイ。わかります？
っていうようなやつはまあこれまあ72年とかもう about 50 years ago ディベロップされて、でまあエッセンシャル この finger hand robot for the hand finger gesture is developed at Stanford University at 1994。ラルクってやつが作られたんだけど、あれなんだけど、それはだいたいこういう感じで。これはワイヤードリブンだと思うんだけどね。ワイヤードリブンメカニズムでなんかフィンガージェスチャーを作りましたよ。スタンフォード大学のやつが、多分最初のファーストハンドロボット to make the finger hand gesture display。あとはATM とかに使われているキャッシュディスペンサーとか ATM とかオートマティックマシンズ、ティケット、ベンダーとかいろんなものに使われているハンドジェスチャーで、アニメーションソフトウェア is for example, this is developed about 10 years ago by Hitachi Corporation, and also some this hand finger gestures learning system, learning software is also developed. You can find this free software. これ10年前はこんなもの。アニメーションですね。こういうやってましたね。はい、これがオートリーパートね。OK。The second is a visual part. Eye. Visual senses looks like this. 角膜、cornea. Outside to protect the eye system, and the crystal lens. Crystal lens is here. Crystal lens is thickness is adjusted by using these muscles. This muscle is ciliary muscle. It is said. So by tending this and changing this thickness, and then this lens is making the position of the centrifugal point is changed. And retina is like this. Retina is contains some nerve cells. Nerve cells is here. Nerve cells is located here. And central retina phobia looks like this because humans, animals' eye looks like this, and the axon is generated from at the beginning. There is inside this axon, and then the one part, all of the axon is concentrated in one part, and it is go to the central brain system. So therefore, in some part of the retina, we have no sensory nerve cells here, around here. So therefore, it is said central retina phobia. No, we cannot see at this part. Yes. The oculus, living creatures oculus. The insect is only some the detection cell to light. Only some light is detected by one nerve cells. And for the squid or octopus's eye is the nerve cell, visual cells and retina. なんだ? So nerve fiber is from the outside. Yes. ここにじゃあ書くと。Human animal eye system looks like this, and the nerve cell なんだけど、the nerve fiber is into the inside case. So therefore, in some part, this nerve cell is concentrated and from one portion, this nerve fiber is concentrated and go to the brain. But for the squid octopus's eye is only some nerve cell is here, and it is directly go to the brain. So therefore, no in squid cell and octopus's eye, there is no blind spot. For the animals and the human beings, this part becomes a blind spot because we have no sensing detector cell in here, around here. ちょっとそれはここにEvolution of Human Eye っていうのを聞くと maybe you should watch this video. This video explain about this. でレティナはこうなっていて、でこれがこっちの方にこうボールがクリスタルがこうあって、so, and the light is applied here and some nerve system is here. Mainly this cell to this cell, two cell, and also this cell. So maybe mainly 5 kinds of nerve cell is here. This 5 kinds of nerve cell is the rod cell, cone cell, horizontal cell, bipolar cell, and amacrine cell. These cells is located like here, and this has some layer, 1 layer, 2nd layer, 3rd layer, 4th layer, and then it is connected to each other by something information processing, and finally this fiber is concentrated at the blind spot and go to the brain. で some part is for the brightness, some part is for the colors, red, green, blue, 3 kinds of cone cell is here, so therefore this part is for the color detection. Rod cell is mainly for the brightness detection, color detection, and horizontal cell, bipolar cell, amacrine cell is some kind of information processing is done around here, and then finally the cell fiber, optic nerve has some axon, and then this action potential is transferred to the brain. ですよ。でそれはちょっとどっかを見れば、例えばレティナストラクチャーとか見ると
As the layers deeper in the eyeball hide the photoreceptors, the light must first go through these layers before it reaches them. The path of the nerve impulse is opposite. It comes from the photoreceptors through bipolar neurons to the ganglionic cells, whose axons exit the eye in the blind spot and form the optic nerve, the second cranial nerve. As it is a normal route of the light in almost the entire retina, there is one point in which the light does not come through the layers of the retina. The fovea centralis is the place in the center of the retina in which the cell's building layers of this tissue are drawn aside
に、レティナがあって、コーンセル、ロットセルとかあって、コーンセルは、for the detection of brightness, and the rod cell is detection for the color. Okay? And then the layer structure is processing, the preliminary processing of the signals, and then some preliminary processed signal is given to the brain. And the ciliary muscle is adjusted to the bifocal adjustment. Accommodation is here. The lens accommodation is if you want, you can see this. Well, this is a fundamental biology. The next part is engineering part. So therefore, the substitution system. One most important substitution system is a Braille block. Braille is here. He is a blind person and he has developed this French person. And the 19th century, at the beginning of the 19th century, this 6-dot system is developed by him. The one alphabet character is expressed by using this dot system. This is also used in the road. Not any meaning, but this is a cross point or something is informed for or you should go straight is informed by this dot system. Okay? And also the dotted printer, this Braille system printer is also commercially available. So therefore, this is one way to detecting some tactile sense system. So the tactile sense is used, and also the auditory sense. Auditory sense is used in place of the visual sense. Then one typical example of the engineering system is optacon. It is called optacon, optical tactile converter. About 1963 in the United States, MIT's engineer Brice and Stanford University's Professor Linville developed this shoulder-held system. One is a CCD camera. CCD camera traces some part of the information, and this binarized information is frequently vibration displaying at here. So that if you touch something on here, that you can see the fact this camera captured. So the binary image by camera, this is a CCD array, and then this part is a part of the A is stimulated on this the mechanical pins. Okay, so therefore this is the actual system. This is shoulder-held system or tabletop system. Desktop system is also commercially available. In 1970, about 50 years ago, in Telesensory System Incorporation is commercial product is shipped. And in Japan, the Canon Corporation is launched as an electrical reading system, Optacon. But this system is stopped manufacturing at 1996, and the maintenance is also finished, and this company is closed in 2005. But you can see some story of this development story, and this why this engineer is Brice and Linville is developed because this Brice's daughter is a blind person, so therefore he wants to make some support system for his daughter. Okay, so this is early research leading to the
To bypass printing in Braille, devices are in development to let the blind read ordinary printed material.
Again,
これね。
Stanford's Dr. Bliss has invented 2 such reading devices.
The first device that we'd like to demonstrate is this array of air-jet tactile stimulators. To explain how one of these tactile stimulators works, consider a box filled with air.
まあいいんだけど、まあこういうシステムを作ったわけね、メカニカルバイブレーションシステム。で、not only mechanical vibration, but also the electrode stimulation system in the back or the stomach or something is also developed. This is the said TVSS. TVSS is tactile vision substitution system. So in 1960s and 1970s in Smith Kettlewell the visual science laboratory in the United States or the group in Japan is developing like this. And also it is also equipped on the wheelchair. The wheelchair electrode array is here, and this makes some stimulation. Some だから、エレクトロードスティミュレーションだったり、なんかメカニカルバイブレーションだったり、それは using some magnet or air pressure pin or the electrical electrode is many times is skin vibration method, skin information method is developed, has been developed. But it is not good enough because practical realization is most of them is failed because very large scale and also small amount of information can be informed to the users by using this kind of large scale system, and the cost is very high, expensive, but the information and some understanding learning skill is necessary to use that.
Tactile vision substitution with smartphone and electro-tactile display.
これはさ、2016 recently some universities teacher in Japan is developed like this system.
Hamsatouch, tactile vision substitution with smartphone and electro-tactile display. According to WHO report in 2012, 285 million people are visually impaired worldwide. 39 million are blind and 246 have low vision. About 90% of them live in developing countries. There were numerous attempts to show surrounding scenes by tactile channels for users with visual disability. However, several issues remain to be solved.
このシステムは、ここのヘッドのところにエレクトロードをこうやってやって、エレクトロードのそのベルトをヘッドベルトをして、このエレクトロードシステムでなんか、このカメラ、ここのグラスについたカメラでキャプチャードイメージ is processed and informed to this head by electrode is one system. This group has been developed.
Especially high cost, unportability, and non-state-of-the-art image processing. To address these issues, we developed Hamsatouch, a novel tactile vision substitution system which is composed of a smartphone, phototransistors, and electro-tactile display. Firstly, we use commonly available smartphone as a camera and an image processing device.
まあだからスマートフォンでキャプチャードカメラでだからバイナライゼーションプロセス is done in this smartphone system. And then this binarization image how to inform to the user.
Reduces hardware costs, and we can easily adopt new imaging technologies, including 3D sensing. Secondly, we use electro-tactile display to present tactile pattern, which dramatically reduces size, cost, and power consumption. Thirdly, we used simple optical data transmission by an LCD and phototransistors, which reduces software cost, since we only need to process image and display it on the LCD.
だからこれはただのスマートフォンのディスプレイにこれを put on this system, so the LCD system capture the white black information, look like this, and then this electrode system is shown to the vibration information to the fingers. っていうようなシステムを作りましたという話です。
The smartphone extracts edges and display to its LCD. The optical sensors receive the image, and the electrotactile display converts it to 32 by 16 tactile pattern. Hamsa-Touch also works without the smartphone by lighting backside LED and used as a reading aid.
まあもちろんデスクトップでも
Tactile vision
使えますよ
substitution with smartphone.
という話でした。OK。で、まあそれはそこまではたくさんのこのタクタイルテレビ、TV とか、まああとこういう、ウルトラソニックセンサーのモワットセンサーとかミニガイとかガイとかこういうシステムがたくさん売られていて、例えばミニガイドっていうのはこういうハンドヘルドタイプのウルトラソニックセンサーで。
The Mini Guide US is a handheld electronic travel device that
どうやって使うかというと、こうやって持ってて、この
potential
searching
clients will have to go through a training
and
session
if some obstacle is detected, some noise or vibration, the user can be captured and then the distance to the obstacle or the direction of the obstacle can be captured by using
After
this.
the auditory demonstration, Justin will instruct playing on the different tactile settings the Mini Guide can be set to.
まあこういう、ハンドヘルドデバイス is also available, but a little bit expensive maybe. まあいろんなタイプが作られました。でももちろんそのアイグラスタイプもあって、バッドセンサーとか言って、ウルトラソニックウェーブアイグラスとかソニックガイドっていう名前で、It is commercially available で、ここに、ウルトラソニックセンサーの、ジェネレーターとディテクターがあって、で、ここに、イヤホンに both right ear and left ear, both ear の、このイヤホンがここにあって、で、capture some obstacles information。これは最近のやつですね。
Center for Research and Advanced Studies in Guadalajara, Mexico, researchers have developed special lenses for the blind. The idea is to turn a traditional pair of glasses into a navigation device to allow users to freely move from a specific point while avoiding both static and moving obstacles. It uses ultrasound technology, sound sensors, GPS guides, and an artificial voice to guide the user. Similar smart glasses have already been developed, but what sets these Mexican-made lenses apart is their use of ultrasound technology to detect translucent objects.
El proyecto de Smart Guide se trata de desarrollar unos lentes inteligentes.
The Smart Guide project is trying to develop intelligent glasses to help visually impaired people in their everyday lives, such as JAWS, recognizing documents, recognizing tickets, colors, and also to help them with their mobility, recognizing obstacles, directions to their destination by GPS, ultrasonic sensors, and via a pair of cameras that process images through the lenses.
Y por medio de un par de cámaras que van procesando la imagen que se ve a través de los lentes.
まあいいや、というのが、まあ、最近の most、recent commercial product。でそれからレーザーケインとか言って、ケインのところにこのレーザーウルトラソニックセンサーがアタッチしてるやつもいろいろたくさん出ていて、レーザーケインとかレーザーケインコマーシャルプロダクトで、ウルトラケインとかバッドケイソナーとか、まあ、ニュージーランドとか UK とか USA カンパニー has been developed。例えばこれ。
Meet Michael, our virtual man, who is demonstrating the ultracane in action in the street. It sends out ultrasonic beams. If these bounce off objects in the vicinity, the ultracane signals to Michael through vibrating buttons in the handle. The different buttons tell him where the obstacle is. The strength of the pulse tells him how far away. He knows immediately if an obstacle is there, and if he needs to change his course to avoid it. No problem. No hesitation. He's on his way.
こういうウルトラケインとかそういうなんかいろんな名前についたソナー system is attached to the cane is also there. And not only the one direction, but also some the near steps and some middle ranges and little bit far ranges. And also the upper side is also detected because this kind of seeding or some the obstacle is very dangerous for the blind person. So therefore, not only one direction, but also the several directions recognition is also considered as a commercial system. ということで、あとはガイドドッグシステムとか、たくさんあるし、さっき見たガイドケインシステムとか、ユニバーシティミシガン。このガイドドッグは、Japanese National Laboratories the work about more than 30 years ago, もう40 years ago ですね。です。こんなのもありました。で、ミシガンとか、で、それで最後に、最近はこのボイスシステムは、これはどっかだっけ、デンマークかダッチだって忘れちゃったけど、This system is also the commercially available, and also that here is an implanted system, is the artificial, ちょっとな、これぐらい見てみようか。
Here in New York today, an apparent breakthrough, albeit a minimal one, in giving sight to people who cannot see. Many researchers have been trying to apply digital technology to the affliction of blindness, but nothing has gone so far as the research you're about to see. One blind man has actually let scientists hook him up to an artificial eye. Here's ABC's Jackson.
This man has been blind for 26 years, but with the help of a brand new device, he is able to navigate a room and even judge his distance from a wall.
Right now, I should be about 5 feet.
This is the first device that has actually provided useful information for a blind patient.
This is how it works. A tiny camera mounted on a pair of glasses relays images to a small computer worn on the belt. The computer turns the images into electronic signals that are sent through the skull to electrodes planted in the brain.
When an electrode is stimulated on the surface of the visual cortex, it produces a dot of light or dots of light called phosphenes.
The dots appear inside a small rectangle the blind person sees, and they outline roughly what he's looking at. In video provided by researchers, the blind subject is able to place a hat on a dummy and even distinguish the letter E.
So I could take a shot and say that this E faces to the left.
But other researchers say the images are far too crude to be widely useful to the blind, and that to make improvements could take 10 or even 20 years of work.
There are many problems that will need to be solved before this is something that is routinely available.
With a device that's implanted in the brain, there are also issues of safety. And the Food and Drug Administration, which researchers have yet to contact, says the device will need long study if it's ever to be approved. Jackson of ABC News, Washington.
でもだからこの人がこの old guy is the first man implanting some electrode inside the brain, and this CCD signal is processed on some system and then fed back to the brain directly. So this guy, about 5 years ago, is the first person. This directly electrode stimulus system is tested in him. And then presently is for example, the Bioengineering system is now commercially available.
We see some waves here.
For Alan's area, many firsts. With wife Carmen at his side, it's his first time seeing the famous Ferris wheel set on a computer.
I definitely see that.
The thing is, he's totally blind. Has been the past 25 years from incurable eye decay called retinitis pigmentosa.
Yeah, I see bars. I see one.
But since February, he's seeing again with his wearable by Los Angeles-based Second Sight. The vision tech firm has been making a so-called bionic eye. It sees simple images.
Don't adjust your picture, there is nothing wrong. That is because you're looking through the eyes of this, the Arcus 2. It costs about $145,000 and is one of the world's most advanced technologies, giving at least some sight to the blind.
what I see is a series of flashes of light, and the brighter ones obviously like a door handle or a doorknob or a frame or something like that. I'll be able to see that that is what it is.
Alan can't see fine features. The Argus 2 is still limited, but he did see his wife this February.
Yes, it's going to take interpretation of the shape.
As the world's 15th person with a prosthesis.
Carmen.
Today, another first. Alan meets Bob Greenberg, the man behind his second sight. His most moving experiences
are the ones where people talk about being more engaged in the world. Social cues that we all take for granted, like can I touch the cheek of my loved one without poking them in the eye? Those kind of interpersonal things, I think, for me, are the most moving.
This is how it works. A camera on a pair of glasses transmits images wirelessly to a layer of 60 tiny electrodes on the retina inside the eyeball. Only about 100 people have had the surgery around the world. So, what do people see? Bob puts me in the simulator.
This is a half moon. This is a triangle. This is a circle. Give it a shot and see what Alan's like.
Bob also checks Alan's vision.
まあいいやというふうにこのダイレクトリーのこのちょっとブレインにエレクトロードをやる場合とこのレティナにエレクトロードをやる場合とありますよねですね。OK? はいということで That's all about the today's class.